Hello and welcome to EngPhys 3 BA3 Lecture 8. This is going to be a lecture where we go over how we're going to solve bipolar transistor circuits. So everything we did in Lecture 7 is all still valid, and in fact arguably more valid than what we're doing in Lecture 8. Lecture 8 is going to be approximate solutions to help you get a feel for how transistors are working as long as they're in their active region. So we're going to basically assume that we're over in these regions, and we're going to look at some circuits where we don't necessarily need to know exactly what beta is in advance, which is good. We just need to know that it's large, and that's going to be true as long as we're staying in the active region where the collector voltage is higher than the base voltage is higher than the emitter voltage. Okay, so assume BJTs are in their active mode, and that the base emitter junction is just a forward bias diode, so 0.6 voltage drop across that. You know, in reality, that's not always exactly 0.6, but this is going to be close enough for us to understand how the circuits work. And that IC which is beta IB, is approximately just equal to the emitter current. Then we're going to solve the circuit and check whether our assumption was right by seeing if the base voltage is at least 0.6 above the emitter voltage with the collector voltage above the emitter voltage still. If not, then the transistor must have been in a cutoff state. So the first of the circuits that we're going to be dealing with is the transistor follower circuit. And that's drawn up like this. This is a transistor follower. It's called that because it uses a transistor, and the output voltage just follows what the input voltage is doing. If you analyze this, you see output voltage is input voltage minus 0.6 because we've got that forward biased diode there. And that's it. Okay, so that seems kind of dumb at first, but this does some amazing things for the output and input impedance. Well, in a normal system, you want the output impedance to be as low as possible and the input impedance to be as high as possible. That way, if you disconnect the next circuit, then it behaves basically. The previous circuit behaves basically the same, and you can connect a bunch of loads to the same output, and you know that that's not going to change what the output voltage was. We've seen this before, so let's look at just a voltage divider. If you were to attach another resistor here on the output, and the resistor, let's imagine it's the same size as this resistor, well, that's really going to change the output voltage that we're getting from this circuit. For this voltage divider setup, what we're going to do instead is look at the input and output impedance from the perspective of this dot here. So this is a little bit weird of a setup to do, and maybe not what you would have guessed, but basically what we're doing is we're saying this is the output impedance of the previous stage, and this would be then the input impedance of the next stage. So we're not kind of looking at the voltage divider itself, we're looking at the voltage divider that's created from the previous stage attached to the next stage. And the reason is we're going to derive kind of a counterintuitive result, which is that the output impedance of a stage is given by the rate of change of its output voltage divided by its with respect to its output current, but negative of that. So here's the deal. If we set up these, if you look at the Ohm's law for this resistor here, the output impedance of the previous stage, then you see that if the output voltage, the actual output voltage goes down, then if this voltage is the same, then the output current should go up for a resistor, and so that's why it's a negative rate of change. That's not true on the input side to the next stage. If the voltage that we're applying goes up, then the current that's going into the input should go up as well. So the reason this one is negative is just because from the output perspective, the output voltage is on the opposite side of the resistor for the drop. So the current's coming out in this direction, and we're looking at the voltage after it's gone through the resistor. Whereas for the input, we're looking at the voltage before it's gone through the resistor, so we have that positive sign there. Okay, let's connect a bad voltage detector to the output of our transistor follower. So this is a voltage detector. A perfect voltage detector would have infinite input impedance, so it's not going to affect the circuit when it's trying to measure voltage. But this is a bad voltage detector, so it's got some input impedance which is pretty low. Let's even imagine that it's much lower than R, so that we can look at this as the entire output now. And what we want to do is look at what the impedance of this circuit appears to be. So what the new input impedance of this is. Okay, so the input impedance is rate of change of the input voltage with respect to the input current, and in that case the input voltage is the base voltage and the input current is the base current, because this is the base is the input, right? Okay, now to find out what this rate of change is, we need to write both of these things in terms of what's going on the other side. So we know the base voltage is equal to the emitter voltage plus 0.6 because of that forward bias diode, and so any change in the base voltage is equal to the change in the emitter voltage. That's just representing the fact that the output is following the input. So what else do we have? We have that the base current is the emitter current divided by 1 plus beta. And we know from the load line on this side that the emitter current is, the change in the emitter current is just the change in the emitter voltage per its resistance. And we're imagining that RL is much smaller than R because it's a really bad voltage detector. So if we just substitute in the numbers that we've figured out there, we find that looking through the transistor, this behaves, this appears to have a load resistance that's magnified by beta. Since beta is large, it looks like the input impedance is much is quite high. So it basically takes what's going on the output side and magnifies it by beta when you look at it from the input side. So because of a small base voltage and current, small base current meaning a big emitter current, we end up having an effectively much higher input impedance by hooking up this follower circuit. Now you can do the same thing and hook up a bad voltage supply on the input side and see how that affects what that changes on the output side of things. So by doing the same kind of a circuit analysis, say there's a 0.6 voltage drop there, and we are going to look at the output impedance of the follower circuit seen from this side. When we hook all of that up, we come up with the output impedance, negative D voltage of the output divided by the current of the output. So calculating the current at the output, we know is the emitter current, which is 1 plus beta times the base current, and then we can relate the base current to the base voltage through its and VI over its load line. So we get the output impedance of the voltage detector being magnified by, being magnified by 1 over 1 plus beta on the output side after it's gone through the follower. So what that means is, looking through the voltage follower here, transistor follower circuit, from the output side, it takes any output impedance of the stage before and divides it by 1 plus beta. So the transistor follower does some, again, does really great things for input and output impedance. If it looks like you've just dropped the voltage by 0.6 and you haven't gained anything for that, but by hooking this up, what it does is it lets you, whatever load you've hooked it up to, it makes it look like that's a much larger input impedance. And whatever was on the previous stage, it makes it appear to be a much smaller output impedance for the next stage. And these are both good things. So the transistor follower has really good properties for input and output impedance, even though it doesn't really do much of anything when it comes to the voltage. Exercise 5.5. Draw a circuit with an imperfect voltage source and impedance Ri connected to a bipolar transistor follower like that shown in 5.9, and the output of that is sent to an imperfect voltage detector with load resistance RL. What's the total change in the detected voltage for a given AC input voltage? So two things. Draw this, which is basically the combination of the previous two circuits we looked at, and then say, suppose that the input changes by some, like we've got some additional AC voltage on the input, and what's the change in the output? So here's a picture of that. We've got some imperfect input, imperfect output, and we want to find out what the change in the output is relative to the change in the input. So we're going to translate the input across this resistance and then drops by 0.6. and that gives us our output, but the current can be split between R and RL. So base current load line gives us this expression, and writing everything in terms of the output. The challenge is to basically get an expression which just expresses expression for the output in terms of the input. Then we can take derivatives. So the emitter current we know is beta IB, or beta times the base current expression that we got up here, but it's also equal to the emitter's load line. So now we've got an expression for that load line in terms of the base load line, and that's great because we've eliminated the emitter and the base current from our expression and come up with the output voltage after solving this equals this is equal to this expression, which depends on beta. Now we don't ideally we can find out what this is without needing to know exactly what beta is, just knowing that beta is large. So sure enough, taking a change in the output voltage by differentiating both sides with respect to VI, we find that the change in output voltage per change in input voltage is, after rearranging, 1 over 1 plus this term dVi. Now if beta is sufficiently large, then this denominator term can be neglected, and so the output voltage change just follows the input voltage change, even though you've got this weird stuff like a resistor for an imperfect voltage supply and this load for an imperfect voltage detector. So that's great. The higher beta is, the better the transistor follower just transmits the input to the output. The 0.6 voltage drop doesn't even matter in AC. Now let's talk about negative feedback. In a lot of the time in real life, negative feedback is seen as a bad thing. So negative means bad feedback, and negative feedback in the colloquial sense would be telling somebody that they're doing terrible, which kind of enforces, sort of stops them from doing what they're doing. In a circuit, negative feedback has a similar connotation. It stops it from changing in the direction it's been changing. And in a circuit, that's usually a good thing. So in systems, negative feedbacks are good, positive feedbacks are bad. Positive feedback would be something that reinforces the behavior that caused it. So a downward spiral in reality where, let's imagine that you go off and commit some crime, and then you decide, okay, well now I'm a criminal, so I better commit more crimes, and now that would be a downward spiral. That's an example of positive feedback in a feedback sense, but we usually don't use that colloquially because positive is seen as a good thing. In circuits, positive feedback bad, negative feedback usually good. So here's an example of negative feedback. Let's see how it works. If we've got a resistor here, which is kind of a variable resistor. So let's see how this works. First, we've got a 0.6 voltage drop there. That sets the emitter current, which is going to be equal to the collector current. So if the load resistance increases, this resistance increases, then the collector current is going to decrease because the resistance went up. So for the same voltage drop, collector current decreases, which decreases the emitter current. But then the base emitter voltage goes up, and that increases the collector current back up again. So it counteracts the change that caused it in the first place. IC goes down, makes IE go down. IE going down makes VR go down, the output across there. So VE, you could also call that. Then that going down makes VBE go up, and VBE go up makes IC go back up again, which counteracts the change that started things. This is negative feedback. So check your understanding. What feedback happens if RL goes down and IC goes up? Well, let's look at that. So if RL goes down, if IC goes up, we have a bigger current down here, which increases the emitter voltage, decreasing VBE, and that decreases IC. So IC going up leads to a sequence of events that leads to IC going down. So it's negative feedback again, still negative feedback. Exercise 5.7. We've got this set up again, and we're told that R is 1K, Vs is 20 volts, Vi is 5 volts, and we're asked to figure out what's the maximum value of the load resistance at which the circuit will work as designed as a constant current source. So this I didn't mention earlier, this is a constant current source. Well, that's how the feedback works. It kind of creates a constant current source. It keeps this the same current no matter what RL is being, because the current is just set by the emitter current, and that's just set by this resistance and the emitter base voltage, so VBE. Okay, so at some point, if we do something to this resistor, then we're going to get to the point where it doesn't work anymore. So specifically, if we start, the bigger this resistor is, the more voltage drop we've got from collector to from the top to the collector, and if that collector voltage gets below the emitter voltage, then it certainly isn't going to be working anymore. So we've got to be keeping in the normal mode. Let's see if we can figure out how that works. Well, the current, so we can say what the current is using this voltage drop there, and the voltage drop across RL is just I times RL. VC has to be above VE for this to be working. So you can solve this set of expressions that you get from that and find out RL must be at least, must be no more than 3.5K. This is a maximum value for RL. If we make RL bigger than this, then we're going to end up with more of a voltage drop, and that's going to lower the collector voltage to below VE, so we won't be in normal mode anymore. Now, another way to look at this exact same circuit is as an amplifier. Let's see why it could be an amplifier if we adjust the resistance values appropriately. So because the collector to emitter current, or the collector current, which basically is the emitter current as well, is much larger than the base current, we can adjust this voltage a little bit to get maybe a big change in the current, and that might change the voltage if we set our resistor values right. So looking at this, suppose R2 is kind of small, then if we increase the voltage here a little bit, we could get a big current change through R2, and that's going to pull a lot of current through R1 as well. So if R1 is quite large compared to R2, we should have a big change in the output voltage from that change there. So let's analyze the circuit in detail and see how that works. So we've got a 0.6 voltage drop across there, and that lets us write the emitter current. And the emitter current is basically the collector current. From the collector load line, we've got that the collector current times R1 has to be equal to Vs minus Vo, which is also Vc. Now, writing that IC is IE, and using the emitter load line, we've got negative Vs at the bottom here. We come up with an expression for the output voltage in terms of the input voltage and the supply voltage. So in DC, this is going to depend on the value of the supply voltage. But if we were to just take a small change in the input voltage, you see this gives us a small change in the output voltage that doesn't depend on these constants over here, which is equal to negative R1 over R2. So this is an inverting amplifier if R1 is bigger than R2, as we kind of described in a more qualitative sense up here when looking at the picture. This circuit also involves negative feedback. So let's imagine that the output voltage goes up. If the output voltage goes up due to whatever else is going on this side of the circuit, then that is going to reduce the drop here. So the collector current goes down. If the collector current goes down, the emitter current goes down, and that increases the VBE, which pulls the collector current back up to increase to decrease the output voltage. So we started with an increase in output voltage, and that led to a decrease in the output voltage, so it's negative feedback once again. Okay, a couple more sections for today. Impedance. We're going to look at this. So for the amplifier, let's figure out if we can calculate the impedance, assuming that there's a load current IL going through the output for the above amplifier circuit. Rewriting the just kind of redoing the expressions before, but also allowing an IL to be leaving the setup. We can say that the Z out is the negative rate of change of V out divided by IL, as per usual, I out. And looking at this expression, it turns out that it's equal to R1. So that's not amplified by beta like it was for the follower, or divided by beta like it was for the follower circuit. So this is just a regular old output impedance. The input impedance, we still get this 1 plus beta set up if you go and work through the math for that one. So the inverting amplifier has great input impedance, but not necessarily so great output impedance, although it is worth noting that R1 is probably quite a bit larger than R2 if you're trying to get a lot of gain for this amplifier. Still, we don't get that beta amplification of the impedance on the output side like we do on the input side. So the input impedance isn't, the input impedance is great, it's nice and high, but the output impedance isn't necessarily as low as we would have liked. Okay, let's talk about some of the limits of the output of this inverting amplifier circuit. So because we still need that VC is higher than VE, and the output cannot possibly go above the top voltage here. So even if we set the current to be 0 in the downward direction, then the output voltage would reach a limiting value of Vs, and if the current reaches kind of a maximum value, then we'd have the output voltage limiting to VE, whatever VE would be at that maximum current value. So you see there's some limits in the output. If we were to take an input AC signal and drive it above, drive it with too big of an amplitude, then we might end up with clipping. So here's just a maple bit of code to demonstrate clipping. You have what would have been a nice sine wave, but the tips are clipped off as if you've gone up to them with hedge clippers and kind of clipped off the top of these nice sine waves. So this is what your output might look like if your input voltage is, if your input amplitude is too high on your AC signal. So now the top part is a little more clipped than the bottom part. Sometimes you may find that just the top parts of the waves are clipped, but the bottom parts are not. In that case, you need to adjust your DC bias voltage to get things a little bit better. So what we definitely want is our supply voltages to be as far apart as possible. Other things equal, that's going to increase the range that we can have on our input signal to get an output signal. But the problem with that is that the bigger the voltage difference is the bigger power, the bigger passive current we're drawing through the transistor. So you don't get that for free. It's going to be draining more power while we're doing that amplification. Either way, though, we want to, maybe the more interesting problem is figuring out where to put the DC point for this input. So where to set the 0 AC voltage point so that we're getting the most range. Like if we were to move this wave down a little bit, then we wouldn't be clipping the top so much, but we might be clipping the bottom a lot if we move it down too much. So where's the optimal point? This is just going to be a solution for that. This is one of the things you need to do in lab 3, although for a slightly different circuit than this. Still the same approach applies. Your optimal voltage is going to be the DC voltage where you have the most range in AC signal. Okay, so what we do is we say the maximum AC input is going to give the minimum output because it's an inverting amplifier, and the minimum output is when the output is VE. And the minimum AC input is when we get the maximum output, which is just Vs. What makes this a little bit complicated is that VE is going to depend on the current. So I encourage you to give a shot to kind of writing those equations and using the ones we had in the previous section. If you do all of that, you'll come up with these two expressions. So at the minimum input, the output voltage is equal to Vs. Now let's say that we're applying an input signal of VDC, where VDC is the optimal DC voltage, and it's going to be offset by a delta VI. Delta VI is the amplitude of the AC signal. So this is our input range from the center point to the edges of the range. The maximum input would be VDC plus delta VI, and the minimum input would be VDC minus delta VI. Okay, so at the minimum input, Substituting in our minimum input of VDC minus delta VI, we've got Vs as the output, and now we'll sub in our input on this side of the equation and get this expression. At the maximum input, we know that the output is equal to the emitter voltage, and the emitter voltage is also equal to the input minus 0.6. So we sub in the maximum input of VDC plus delta VI to both sides of this expression. Now we've got two equations and two unknowns, VDC and delta VI. You can solve those and come up with where you should put the DC bias voltage and what the input amplitude you can get for that is. So as promised, with higher Vs, you can get bigger amplitude, and the location that you should put the DC bias voltage depends on this 0.6 voltage drop and the values of the resistances and also Vs. The maximum swing of the output voltage is delta VI, and it's multiplied by the amplification factor. So rather, the maximum swing of the output voltage is the input swing multiplied by the amplification factor. So for this input voltage, what's the maximum output voltage swing that we would be able to get? Sometimes you're interested in that as well. And so we'll just multiply the input by the amplification factor. And that means that the R2s will cancel and we'll end up with Vs R1 over R1 plus R2. So when R1 is much bigger than R2, which is the case for large amplification, then the input should be biased at where? Negative Vs plus 0.6 volts, and the output would swing relative to V equals 0. So the input bias voltage will end up needing to be negative Vs, and we'll get an output swing equal to just the value of the supply voltage. That's the case where we've got positive Vs at the top and negative Vs at the bottom. We'll do an exercise where we resolve this for the case that's closer to what you do in the lab, where you have 0 volts at the bottom. Exercise 5.2.4. Here's a circuit configuration known as a Darlington transistor configuration. It still has 3 terminals, so we've got 1, 2, 3. It behaves like a standard BJT, but with an effectively much higher beta. Calculate the input impedance of a follower made using this circuit element in place of a single transistor. So a reminder that that a follower, where was that? Transistor follower circuit, here we go, was this circuit. So instead of this transistor right there, we're going to make a follower using the Darlington in place of that. So we've got a load resistor here on the emitter, and we want to find out the input impedance, so how this load resistor is viewed through that base. If this really behaves like a much higher beta, it's kind of going through 2 transistors, right? So our guess is that the input impedance should be beta squared times that load resistor. So if going through 1 transistor gets you beta times it, going through 2 should get you beta squared times that. Let's just see if that works. We can use all the approximate calculations in this section. So we'll say this is 0.6 voltage, a 0.6 volt drop, and a 0.6 volt drop from there to there. So we know, okay, well, R has 0.6 volts across it because it's just connected across that base emitter junction. And so that tells us how much current goes down there versus goes in there. We can write out IB1, IB2, and the collector currents are just whatever they would need to be equal to the basically to the emitter current. So where does this emitter current go? The emitter current from transistor 1 goes partly into the base current for transistor 2 and partly into the resistor here. And then they meet up after the other side. So this one being the portion of it that goes through there is multiplied by beta again as it goes down to there. Then it combines with this current to give you the output current. So writing all of those things, I encourage you to go through the math if you like. And sure enough, we have the input impedance does end up being beta squared times that output load impedance. Design a non-inverting amplifier with the gain of 5 using bipolar transistors. Whoops, showing you the answer. Anyway, cascade 2 inverting amplifiers, one with a gain of -1 and the other with a gain of -5. So you just need, or any real combination that gives you gives you a product of +5. That's all that is. Exercise 527. What would happen to the output of this circuit as the input is increased from 0? And why would this generally be a bad design for a transistor circuit? Well, this is just a diode. So the base current would go from being extremely small to suddenly extremely large. We're not doing anything to limit the base current. You definitely need a resistor on at least the emitter or the base. Having a resistor on neither of them and just on the collector is not a good circuit design. We'd probably blow up our transistor if we tried to do this. Okay, when we looked at the basic inverting amplifier, this CE amplifier from earlier, we were first looking at things with a positive VS and a negative VS as our two supply voltages. But now we're going to look at a different situation where the bottom is grounded and we've still got positive VS up here. And in fact, we're also going to look at some of the things you might put on either side of this to make a decent circuit here. So we've got a voltage divider that we're going to choose the values of to set the optimum bias voltage, optimum DC bias voltage, and then we've got capacitors to isolate our input and output from this from these bias points. So this is the capacitors are going to serve to basically turn this into a high pass filter from input to output to only allow our AC signals through this transistor inverting amplifier here. Okay, so we can redo some of the analysis from before and come up with our output voltage, at least at this point here, relative to the input voltage here. And the expression that we get is similar to the expression we had earlier when we had a top voltage and a bottom voltage. So let's compare that. The expression we got then was this one. And now we've got this expression. So let me just copy the previous one so we can compare it on the same screen. Okay, so basically the output is almost the same as before, except we don't get this VS negative R1 over R2 term. So that one's gone. We've got just the top VS part. And we're actually going to lose all of this stuff as soon as we go through the capacitors anyway. So that's something that doesn't really matter all that much. But we still do need to consider what the maximum range of this signal could be to avoid clipping. And so you'd want to consider that when you decide what your DC bias point should be by picking these two resistors. If you redo the calculations that we did in the clipping section, and we're going to do that in an example, then you'll find that the optimum DC bias point is this, and the maximum the maximum input swing that we're allowed is this. So the maximum input swing calculations, if we compare these two expressions to the ones we got in the clipping section, I'll just copy those and then bring those down here. So these are the two that we had in the clipping section. You'll notice that the input swing is about half of what it was before. That kind of makes sense because before the total voltage difference between the top and the bottom was 2 VS, right? It was VS at the top and negative VS at the bottom. And so now we've kind of divided the supply voltage difference in half, and so our input amplitude is divided in half as well. The optimum DC bias point is a little bit more complicated than that. This interestingly works out to give us a negative sign in there in terms of our optimum DC bias point, and is based on different resistors. At least before it did that. So when we had the bottom voltage at negative VS, then the optimum DC bias point turns out to be close to a very negative value. Here, though, the voltage, we definitely don't want it to go negative, because if the input voltage is negative, it would definitely be below the emitter, and so the diode would be reversed biased. So notice that the resistors have changed places here, whereas for large gain, we want R1 much bigger than R2. So before, we had this basically at negative Vs plus a 0.6. Now R2 is in the numerator rather than R1. So this is kind of a small number, and this for a large gain limits to 0 plus 0.6. So it's still kind of the bottom voltage plus 0.6, but a little bit changed by that, by the value of the resistors. So that makes sense. Okay, let's do a design exercise for an inverting amplifier circuit up here. So if we wanted to, let's suppose we've got some criteria. So we've got this circuit. We're going to build a circuit like this, an inverting amplifier. And what we want to do is get an amplification factor of 10. We know our input frequencies are going to be in the megahertz range, and we know we're going to have a load impedance of 50 ohms and a supply voltage of 20 volts DC. So these are our constraints. Let's pick things that are going to work. So first thing we can do, because we know the load impedance, we can pick the value of the capacitor so that we've got a good high-pass filter that's going to stop frequencies that are, let's say, a factor of 10 below the range we're working in. We're working in the megahertz range, so we want to stop frequencies around 100,000. So that means the omega is about 10 to the 6 hertz. And so we'll just set the tau of this low-pass filter to be appropriately 1 over that, 1 over the omega. And that tells us what our capacitor should be, about 0.02 microfarad. That gives us a ballpark for what we want that capacitor to be. Okay, then let's match the impedance of this resistor to this resistor. The reason we want to do that is so that we'll have about the same power dissipated in this resistor as this resistor. So if we make this resistor too high, then most of the then we're going to be modifying the voltage a lot by the load. If we make this resistor too low, then most of the power is going to be from the voltage drop across that. So we don't want either of those situations. So we have to make the resistor, a good balance is to make it the same size as this resistor and then work from there. Okay, so R1 has to also be 50 ohms. Now we're also told we wanted an amplification factor of 10. And we know that the amplification factor is R1 divided by R2. So if this is 50 ohms, then that means R2 has to be 5 ohms, so that 50 over 5 is going to give us a 10. Now we need to pick our DC offset level. So what voltage do we want here in DC, which is going to help us decide on our voltage divider resistors. So from the calculation we did in the last section, we know that this is our DC offset voltage equation. Based on the output resistors that we had there, or the gain resistors for the amplifier, we end up with this as our DC offset voltage, 1.5 volts. So the voltage divider needs to give us 1.5, and the top voltage is 20. So we need R4 over R3 plus R4 to be 0.075. Which values of the resistance should we pick? We don't want them to be too low, because then we're just going to be draining a lot of power through those resistors from the 20 volts that are across them. But we also don't want them to be too high. We need them to be low compared to the input impedance of the amplifier. So these resistors need to be low compared to that, so that they're not gonna, so that this circuit is not going to be affecting the voltage and will be moving around the voltage set point. We don't want that, so we need these to be low compared to that input impedance. And you know the input impedance is R2 multiplied by beta from work that we've done earlier. So if beta is about 100, then we expect that the input impedance of that transistor is about 500. So we need these two resistors to be low compared to that. So to be low compared to 500, let's say about R4 is 5 and R3 is 60 ohms. This is going to satisfy our constraints that they're low compared to 500, and that their ratio in this in the divider gives us 0.075, so that we'll have a 1.5 volt bias. Okay, now let's figure out how much power we're draining to do all of this. Power dissipated through R3 would be based on the current through R3 and R4. Since R3 is a much larger resistance value, but it's got the same current going through it as R4 does, we might be worried that we're draining too much power in R3. So let's calculate that. In R3, we are draining about 5 watts, so we need to check that with the resistor data sheet to make sure that that's safe. And what about the power through the transistor? That's another thing to be concerned with. To do that, we're going to figure out the voltage drop across the transistor, so the collector emitter voltage, and then the current going through the transistor as well. How do we figure that out? Well, we know the emitter voltage is the input voltage, which we've set by our DC bias point at 1.5 volts, minus the voltage drop from base to emitter, which is 0.6. So the emitter voltage is 0.9 volts. And since that's just applied across R2, we can calculate the current through R2. We can say that that's the same as the current through R1, and then figure out the collector voltage. Now we'll know the current going through the transistor from collector to emitter, and we'll also know the voltage of the collector relative to the emitter, so we can multiply the current through it by the voltage across it to get the power dissipated in the transistor. Okay, doing all of that, we come up with 1.8 watts, and we'd need to compare that with the transistor data sheet to see if that's a safe operating point for the particular transistor that we're using. Okay, next, the final thing we need to do is figure out the size of the input capacitor to use. Now, this is a little bit more complicated than the output RC filter. So for the input RC filter, we still want to stop frequencies that are, say, below 100,000 from going into the circuit. But what's the resistance that we use? Well, from thinking about Thevenin equivalent type things, we've got a resistance in AC here of this resistor to ground. The fact that this is a DC voltage in AC, that still, it looks like, kind of like a zero. So we've got it in this in parallel with R3, in parallel with beta R2. But beta R2 is much bigger than those two, so let's ignore that one and just look at R4 in parallel with R3. And so that's the effective resistance that we use with the capacitor to set our high-pass filter. Remember, if we wanted, like in the first step, if we wanted the frequencies below 100,000 to be cut off, then we want the angular frequencies below about 1,000,000 hertz to be cut off, which means we want a time constant of about 1 microsecond. So dividing that time constant by the resistance of 4.6 ohms, we end up with C1 is 0.2 microfarads. Okay, some exercises now to just close off everything we've been talking about. Exercise 5.9 asks us to prove result 5.3.16, which was the new set of DC bias point for the situation where we've got 0 volts on the bottom rather than negative Vs. So first exercise is to prove that. Give that a shot. So what you do is, as before, you come up with your output expression in terms of your input expression. You can go and rederive that if you want, or you can start from this point and then just figure out what the midpoint of the possible input range is. So what determines the maximum input and output range? The maximum input range would correspond to the minimum output, which is where the output, where the collector voltage is the emitter voltage. The minimum input is the maximum output, which is where the collector voltage is Vs. Setting both of those constraints up, you can rederive that expression. Exactly the same as we did before. Exercise 5.10. What's the input impedance of the circuit shown in figure 5.14? What part of the circuit's important in this calculation? So this just goes back to the inverting amplifier with the bias point again. So, but now from this perspective, what's the input impedance? You're going to have to consider the impedance of the capacitors and the impedance of the transistor there. So before we said, okay, let's just, we were looking at this perspective and we calculated the effective resistance seen by the capacitor in this RC filter. And we said, okay, let's ignore this impedance because it's quite large compared to these two. And if you want to look in terms of complex impedance, there may be some other effects of what's going on this output that might be seen on the input, but those are going to be even smaller than this impedance change. So let's just say that the impedance of the transistor is large and see if you can figure that out. Okay, so using node equations, if you like, or just saying we've got those impedance sources in parallel, we end up with kind of a capacitor impedance in series with the resistors R3 and R4 and Zin all in parallel. And in the limit of high Zin, that turns into this expression. So the impedance ends up just being as promised. You can derive that it's just the capacitor in series with those two resistors in parallel. So only the circuit elements on the input side of the transistor contribute. One more example. This is an exercise where you get to redo the gain calculation, but under a different set of parameters. So design a circuit that will have an AC gain of 10, same as before, with maximum possible swing of the output without clipping, using one voltage source and one bipolar transistor, like we did, which will have a frequency response in the 10 kilohertz range or greater. So now we want to be able to look at signals that are 10 kilohertz or higher. This is exactly the same as the previous setup, just that our capacitors are going to be a little bit different. So we're still going to have the same bias point and the same set of resistors because the gain was the same, and the load resistance we're going to assume is the same just so that we can use the same numbers as last time. We'll come up with exactly the same answers for pretty much everything except for the capacitors. And that's it. That should get you started well on what we're doing for BJTs in the lab. And that's pretty much the end of BJTs, except for looking at this beautiful circuit here when we're introducing op amps in the next lecture.